So this is, remember what the parent graph looks like. So the parent graph is, let's just call it P of X for parent, is 1 over X. So what transformations have occurred here? What was that? Very good. Left 2 and down 2. Here's the left 2. That's essentially what happened is P of X plus 2. So we plugged an X plus 2 in and then subtracted 2 after the fact. So there's our left 2 and there is our down 2. Now, when you shift with asymptotes being involved, I highly recommend you first kind of look at where your new asymptotes are. So starting with the proper order of transformations here, everything's going to move left 2. Now the x-axis asymptote, when you move that left 2 units, it doesn't change, does it? Right? Horizontal line left 2 units doesn't change. But a vertical asymptote left 2 units definitely is going to be in a new location. And then when things shift down to, the vertical one is going to be unaffected, and the horizontal one will be affected and move down too. So what it sort of gives us is a new set of X and Y axes, for lack of a better word. And so now, like a new origin, our full origin got shifted, and then there was no stretch or compression. So do you guys pick up on the fact that on the parent graph of a rational, you always have the 0.11, right? So we're going to kind of keep that same 0.11, but with respect to our new origin after the shifting. So this 1 would be there, and kind of draw that in. And then also it has a 1, -1, so with respect to our new origin, I would draw that. And outside of that, it's just a sketch. So I'm going to go with this marker because I think it will be easier to see. There's going to be some overlapping, so it obviously can look confusing. But does that make sense? Okay? Stephen. Yep. Yep. And now if there's a reflection, there's going to be more to it. But as far as just shifts are always going to change your old axes to sort of a new set of axes and a new origin frame of reference. Okay? Now that is the thought process from a transformation perspective. If we go back and think about what we talked about on Friday, and forget about this, just looking at the equation, where is the vertical asymptote? X equals -2. And sure enough, our shift left 2 units created that same thing. So those ideas, even though you're thinking about them from different vantage points, they both leave you with a vertical asymptote at -2, whether you think of it from a shift perspective or you think of it from just kind of that undefined perspective. And your horizontal asymptote, so this is the thing about horizontal asymptotes. The big over small, small over big rules that we looked at, they only apply to like the core of the rational function. So the numerator technically has a degree of what? 0. The denominator has a degree of 1. So that would be a small over big scenario, which would be a horizontal asymptote at the x-axis, yes? But then when you shift it down 2, that moves that down to just y equals -2. Correct. Yep, so he's saying if this core of it showed a horizontal asymptote, if it was same over same, and it was a coefficient of 4 over a coefficient of 2, and so your horizontal asymptote was 4 over 2, and your horizontal asymptote was at 2, and then you had this -2 after the fact, that would shift it down 2, so then it would now be at the x-axis. Good question, Stephen. Big over small does not exist. there's no horizontal asymptote in that case. Okay? All right. This one over here has a different parent graph, okay? Here is this parent graph. It's still a rational function, but the parent graph looks like that. The parent graph function would look like that. How's it different, would you say, Liz, than the other parent graph? Right. Instead of quadrant 1 and 3, it's in quadrants 1 and 2. Looking at the equation, the main difference is your denominator is squared over here. Okay? So this is a new concept that's going to get us talking about the degree of the asymptote. Similar to the way we talked about the degree of the zeros, right? First degree 0, the line would just go through the x-axis. A second degree 0, we get a bounce. A third degree 0, we get a wiggle. So that's kind of degree rules from a 0. We have similar degree rules for asymptotes. And it has to do with the behavior as you approach the asymptote. So let's look over here. This asymptote, right, because the factor was x plus 2, only had a degree of 1. And because it had an odd degree, the behavior approaching the asymptote is opposite. So on one side it heads towards positive infinity, but when it's coming from the other side it goes towards negative infinity. Those are shooting in opposite directions on either side of the asymptote because the asymptote is odd. Over here we have an asymptote that's even, and the behavior on either side of the asymptote is both the same. Does that make sense? Yes? No? Maybe? Stephen? There is an element of even odd floating around in here. But once transformations get thrown in there, it's not going to be symmetrical to the origin. Although if you're talking about your new origin, yes. Yes and no. For the parent graph, yes. But this is no longer an odd function. Because once you move it, it still needs to be truly symmetrical to the original origin, and it's not. So you're throwing in a different twist and idea there, that there is an element of that floating around, but that's not really what I'm trying to say. I'm not going to probably look into that too much because your symmetry is the same. This new function is not odd. It's not an odd function. That is not symmetrical to the original origin. The parent graph was. So that's happening. But I'm more talking about the behavior, and we talked on Friday. The behavior as you approach any vertical asymptote always shoots off towards some infinity, whether you're approaching it from the left or from the right. If the degree of your asymptote is 1, one's going to go, then on one side it's going to go towards positive infinity, and on the other side it's going to go to the opposite, negative infinity. Versus if the degree of your asymptote is even, they're going to either both go to positive infinity or they're both going to go to negative infinity. They're going to work together as opposed to being opposite behavior. Does this make sense? Okay? So this is our parent graph for 1 over x squared. So kind of add that to your bank of what parent graphs look like. Like any parent graph, and I actually remember doing this in my junior year of high school when there were so many parent graphs to remember and I couldn't really remember them all. You can always just quick plug in a couple points and just remember, and like once you plug in 1 and 2 and 3 and -1 and -2 and -3, you'll immediately get a few points and you'll remember, oh yeah, that's what that one looks like if you're ever, at a loss. It's just one strategy would just be to plug in a couple points to jog your memory. So that being the parent graph, what transformations are occurring? Jack, can you tell me the first transformation? Yeah, that's right 3, which is going to move our vertical asymptote over here. And then, Jalen, what's this guy? Up to, which is going to move our horizontal. And that's our quote-unquote new origin. And so we'll just sketch our parent graph 1, 1 and negative 1, 1. Sketch your parent graph surrounding that new frame of reference. You know what I just thought that might be an interesting thing to show? If I take h of x and I'm just going to rewrite it to show this, I think something will happen. I can rewrite this, right? I could get a common denominator and combine this into one rational function rather than having this little itty-bitty portion of a rational and then adding 2 afterwards. I could put this 2 over 1 and just rewrite this fraction or this function differently by getting a common denominator. So this would need an x minus 3 squared, and this would need an x minus 3 squared. Agreed? Does everyone see that? Okay. So when I simplify, I'm going to have 1 plus 2 times, and when I square that out, x squared minus 6x plus 9. All over x minus 3 squared is my common denominator. When I distribute, I'm going to have 2x squared minus 12x plus 18 plus the one that's already there will be a plus 19 up top. And when I square out my denominator, I'm going to get x squared minus 6x plus 9. That's just a different version of h of x. Now what's your horizontal asymptote rule? Same over same. And so you should go with the coefficient rule of 2 over 1. So you should have a horizontal asymptote at y equals 2 over 1 or 2, which we can all agree is what we have. Yes? Does that make sense? Nice little connection, I hope. I don't know if I've ever done that to prove to myself that horizontal asymptote rule is still legit. But now we have. So hopefully that makes sense. Any questions on that? Okay. So graphing each rational function, and these are all kind of back to a place where we cannot do that parent graph transformation way. We have to do it more like the way we did it on Friday. So starting with this first one, we always want to start by factoring and canceling if we can to see about vertical asymptotes versus holes. Nothing cancels, so we have no holes. But we do have vertical asymptotes, so we'll start there. Our vertical asymptotes are where? Haley. Yep, x equals plus or minus 3. So we can get both of those in on our graph. Horizontal asymptotes. Take a minute, think about what you think the horizontal asymptotes are. I want to know what Zach thinks. Yep, y equals 4, perfect. So we'll throw that in there. Now, when you have multiple vertical asymptotes, oh, by the way, we would never have 2 horizontal asymptotes, right? You only always have 1 horizontal asymptote, if any, right? Because we obviously have seen examples where none exist. but we have only one horizontal asymptote. You can have an infinite number of vertical asymptotes. You could go on and on forever. So it doesn't create one new origin for us, it kind of creates two. So we have to figure out what's happening to the left of the asymptote, what's happening between the asymptotes, and what's happening to the right of the asymptote. So once we're done here, one of my favorite places to then go is to your intercepts, particularly your y-intercept. So if I want to find my y-intercept, I set x equal to 0, right? And if x equals 0, what does y equal? What's f of 0? If I plug in 0, I'm going to get 0 over negative 9. 0 divided by anything is 0. So my y-intercept is 0. Okay? X-intercepts are going to be a little bit trickier because you're not always going to be able to solve necessarily. But here we can. If we set our function and set our y equal to 0, it's 0 equals 4x squared over x squared minus 9. The only way a fraction is going to equal 0, we talked about on Friday, is when the what? What's the only way a fraction equals 0? If the numerator is 0. And this numerator will be 0 at an x value of 0, which we've already accounted for. And so we can actually assume then that there are no other x-intercepts. They would have surfaced. Okay? And so we don't have any more. So let's now, that's all we really have. Now, you can always plug in points, definitely, and we will do some of that. But my bigger interest is what's going to happen as I approach this vertical asymptote from the left, let's say. So coming off of this point, if I plug in a number like 2, if I just plug in 2 quickly, so you could keep a running list for these or you could do them in your head. If I plug in 2, I'm going to get 4 times 4 is 16 over 4 minus 9 is negative 5. What's that value approximately? Negative 3 point something. So if I go 2 and negative 1, 2, 3, a little bit past negative 3, that puts me there. So already I think I can see as we approach this asymptote, is it going towards positive infinity or negative infinity? It appears that it's going towards negative infinity. So we could do something like this. If you wanted added confirmation, you could kind of, and again, you don't have a calculator, so you're not going to be able to do this directly, but you could think about what happens if I plug in 2.999. And again, here I don't think it's really necessary. I think it's already clear that it's going towards negative infinity. But if I plug that in, x is pretty much approaching 3, right? So the numerator is going to be approximately 4 times 3 squared, which is 4 times 9, 36. And your denominator, what is your denominator approaching as x is getting closer and closer to 3? It's approaching 0. It can't actually be 0, but it's approaching 0. So I'll have like something like 8.99999 minus 9, right? So it'll be like a negative 0.0001. Can you see how the value of that is going to be a huge negative number? 36 divided by a tiny, tiny negative fraction. That negative 0.0001 is going to go into 36 a boatload of times. Yes? Hence the negative infinity that we are seeming to get. Does that make sense? Okay? You don't have a calculator. You cannot verbatim plug in 2.999, but you can definitely wrap your head around the behavior and what's happening. Does this make sense? Okay. So that's there. How about if we head this direction towards negative 3? So if I plug in negative 2, I'm going to get the same on the top, 16, and I'm going to get the same on the bottom. Yes? Okay? So that value, negative 2, is approximately negative 3 point something as well. And if I showed a similar thing and plugged in negative 2.99999, I'm going to get a similar negative infinity look. So let's talk about what Stephen said earlier, even or odd. Even though we don't even see the whole graph, look at the function. If I plug in negative x, let me do that down here, f of negative x, I'm going to get 4 times negative x squared over negative x squared minus 9. I'm going to get back the exact original function, which means this is even. So we should have symmetry to the y-axis. Good. Little things that you know that can help you sketch an appropriate graph. Okay? So from here, what was the degree of this asymptote at positive 3? What's the degree of this asymptote? What power is this x minus 3 factor raised to? The first power. So given that it has an odd degree, if coming from the left it's going towards negative infinity, then coming from the right it's going to go towards positive infinity. Does this make sense? Because of that degree of 1. If you ever doubted it, you could plug in 4 and see that it's going to be over here. You could plug in 3.001 just to get a feel, and it's going to be positive infinity. Okay? If you want to plug in 4 just for accuracy, you also may do that. So 4 times 4 squared is 16 times 4, 64 over 4 squared minus 9. 16 minus 9 is 7. 64 divided by 7 goes in 9 and change, right? So 4 and then a little past 9. So we know based on the degree of our asymptote that that's going to head towards positive infinity. And then end behavior is dictated by the horizontal asymptote. Yes? So without much accuracy, we don't need, these are just sketches, so we wouldn't want the general look. As you go towards positive infinity, your graph is going to approach the horizontal axis. Does this look okay to you? Any questions? And because we have that symmetry, or because we also know that this vertical asymptote has a degree of 1, the similar behavior is going to happen on this other side. And we're going to have the overall graph symmetrical to the y-axis because of that even behavior. You've got asymptotes with a degree of 1 each, and so the behavior as far as positive infinity and negative infinity is opposite on either side. Okay? Again, these are sketches. The main things that have to be correct are like your y-intercept. If your x-intercepts are clear numbers, then I would look for that too. The behavior on either side of the asymptotes. I'll pretty much look at a graph and see these 6 different quadrants that our asymptotes make. I'll make sure your asymptotes are in the right spot, and then I'll make sure your quadrants are filled with the right sketch. But they are sketches, so don't get overly caught up with perfection on points like 4 and then 9 point something. Okay? All right, next one. I actually want to jump to C. If we have time, we'll go back to B. So, how about vertical asymptotes on C? There are none. There are no vertical asymptotes. How about, so we can do that, vertical asymptotes do not exist. There is no scenario in which our denominator is 0. How about horizontal asymptotes on C? No. There are none. This is a big over small. 4th degree over 2nd degree. So that's not good. right? That gives us less guidance. How about a y-intercept? We get something from there when x equals 0. What do I have? 0. Okay, at least we get some point. X-intercept, obviously we already have at least one of those, right? So x-intercept is when h of x equals 0. But unfortunately, there's only one x-intercept, and it's right there. So how about a case like this, where we don't have asymptotes to approach? Unfortunately, you have no choice but to do a table of values. Okay? So for just a couple, just to get general behavior. So if I did h of 1, 2 times 1 is 1 to the 4th is 2. 1 squared plus 1 is 2. 2 over 2 is 1. Did I do that right? So we got the point 1, 1. How about h of 2? If I plug in 2, 2 to the 4th power is 16 times 2 is 32. 2 squared is 4 plus 1 is 5. This one gives me 6 and 2/5. So 6 and change. So 2 and 1, 2, 3, 4, 5, 6 and change. How about even odd behavior? We could also plug in -1 and -2, but we're going to get the same numbers, right? Because this is an even function. Does everybody agree with that? Okay. So I can do the symmetrical behavior, -1, 1, and then -2 with 6 and 2/5. Okay? So here's something I need to elaborate on. If there is no horizontal asymptote, there is still an asymptote, it's just not horizontal. If you look at the bottom, it's what we will call a slant asymptote. So it's just a diagonal asymptote. It's not horizontal, it's diagonal. So it's a line. It's got to be some equation of a line, just that's kind of like a diagonal line. Yes? That was a 2, right? That wasn't a 3. It was over x squared, right? Okay. So how do you find the slant asymptote? You do the long division. So another application of long division. So down here I'm going to do the long division. 2x to the 4th plus 0x cubed plus 0x squared plus 0x plus 0 divided by x squared, I'll throw in the plus 0x plus 1. So let's do that long division. X squared times what is 2x to the 4th? Oh, this one's even more fun. 2x squared times x squared is 2x to the 4th. I lied, it's not going to be a linear. Maybe that's why they don't call them linear asymptotes. We do our subtraction. Those cancel, those cancel. 0x squared minus 2x squared is negative 2x squared. You can bring down your plus 0x if you want to. Repeat, x squared times what is negative 2x squared? X squared times what is negative 2x squared? Negative 2. Line it up. Negative 2x squared plus 0x minus 2. Do your subtraction. So I should have brought down my plus 0 too. That cancels, that cancels. 0 minus negative 2 is 4. And that's my remainder. The remainder here is completely... Sorry. My bad. I was never good at math. No, it's not. That's where my head was wrapped up in the double sign. 0 minus negative 2 is 2. Okay. Regardless, your remainder here means nothing. This is your asymptote. It's actually not a linear, it's a quadratic asymptote, which is odd. But as you go off and your end behavior, you keep kind of examining your end behavior, it's going to go along the parabola 2x squared minus 2. So I'm going to show you this on your calculator to give you a closer look. We can already kind of see the quadratic-ish behavior. Does that make sense? But the function, this function, and this asymptote, quadratic asymptote, are different. But like I said on Friday, a horizontal, and now as you're seeing, these slant asymptotes, which normally are lines, but because there was a degree separation here, and it ended up dividing out to be a quadratic asymptote, they just guide end behavior. So let me graph the original, 2x to the 4th divided by x squared plus 1. I'm just going to do a zoom 6. Okay, that's pretty much what we graphed, which anybody just looking at that would think that that's a quadratic. And it pretty much is. If you actually divided that out like we did, it is a quadratic. It might actually be the exact same graph. Y equals, I don't remember this from last year. I wonder if I maybe say copying it, but regardless, we're going to do it. Okay, so they're not the exact same graph, but as you get more towards their end behavior, they look like they become the same graph, right? Does that make sense? That's because the actual graph that we are supposed to be plotting has that kind of infinity asymptote where it's getting closer and closer and pretty much jiving with this asymptote. Does that make sense? Without actually ever being the exact same, or is it? If I plug in, let me do this. Okay. I just took a look at the table. So as you get towards infinity, and it happens rather quickly, here's our actual function output, like 6, 70.054, and here's the actual output of the quadratic, right? They're not exactly the same, but they end up being pretty close. And as you go off towards positive infinity, even by the time you get to 12, these are only off by 1/100th, right? These were off by 5/100ths. So immediately, it's not off by much, but obviously the closer you get to infinity, and eventually, because our calculator doesn't have much space to show, eventually they're going to end up looking like they're the exact same value, because they're probably only off by 1/1000th or 1/10,000th. Does that make sense? Why aren't they exactly the same? Why is this one not exactly the same as this one? Very good. Yes. It has a remainder. This one has a remainder. Not a big one, so it's only off by a teeny tiny bit. But again, if you don't have a horizontal asymptote, there are such a things as diagonal asymptotes or quadratic type asymptotes that this graph approaches but never crosses. It's just interesting. I will be honest with you. What are you doing? We have 5 minutes left? Crazy kids. Like you ever think Mrs. Rahal wastes 5 minutes. You're nuts. Being honest with you, that concept of slant asymptotes and asymptotes that you have to come up with via long division doesn't come up often, but it is a thing, and it's kind of interesting, cool. Maybe I just think that. But if you do not have a horizontal asymptote, you still have an asymptote. It's either a diagonal or a quadratic, could even be a cubic. You do have an asymptote. It's just you have to find it via long division. Is that clear? Okay. So this one ends up sort of just looking like a quadratic. And like I said on Friday, if there is no horizontal asymptote, your end behavior will shoot off towards infinity or negative infinity, like your polynomial functions do as well. All right, last one here. We need to factor first. What are my factors of my denominator, Connor? Very good. So I have vertical asymptotes at x equals 2 and at x equals negative 1, so I can get those on my paper. Now I can already tell this is not even because my asymptotes aren't symmetrical to the y-axis. And sure enough, if you plugged in negative x, it's not going to be even or odd. Horizontal asymptotes, we have small over big. So that's an asymptote at y equals 0. Y-intercepts, plug in 0. You're going to get negative 2 over negative 2, which is at 1. So you have a y-intercept at 1. That gives us a point there. How about x-intercepts? When will this whole function equal 0? When will negative 2 over the polynomial equal 0? Never, right? The only way a function can equal 0 is a rational is if the numerator is 0. And if the numerator has a number there, then it's never going to be 0. Okay? So no x-intercepts exist. So that's good to know. It's never going to cross, and we know it sometimes we can cross a horizontal asymptote, but this one is not going to touch the horizontal asymptote. So without plugging in points, if I know that this can never cross the x-axis, I pretty much know that which infinity is this going to approach as you approach the asymptote? Positive. And which infinity is it going to approach as it approaches this other asymptote? Positive. So it's going to do something like that. And what is the degree of this asymptote? 1. So is it going to go towards positive infinity on this side or negative infinity? Which one? Is it going to go in the same direction as this one and both go towards positive infinity? Right. It's going to be opposite because that had a degree of 1. So we're going to kind of be nestled in that corner, much like most rational functions do. They kind of nestle themselves in a little corner of the axes. And then likewise on this side, this is also a degree of 1 on this asymptote. So since this coming from the right, you go towards positive infinity. Coming from the left, you're going to go towards negative infinity. And then your end behavior is guided along the horizontal axis. The more you do of these, the more you'll kind of get used to and comfortable with those behaviors. And there are certainly multiple ways of looking at each problem. But for now, just take your time, get comfortable, do quality sketches. You can use your calculator on your